Hello everybody, welcome to Differentiation Part 2. In this video what we'll be looking at is the application of differentiation. So there's a few new ideas we need to explore. Let's begin just with notation. Let's look at the second differential. So if we've got y equals 3x squared plus 2x dy over dx, so we're going to differentiate this, which is the gradient of y. Bring the power down, so we've got 2 times 3, x2 take away 1, plus 2. In fact, what I'm going to do is add a constant in there. Let's put a 4, and that 4 disappears. And that's what we get. So let's tidy that up. So you've got 6x to the power of 1 plus 2. Now, one of the things we can do is differentiate this again. If we're going to differentiate this again, we'll write d squared y of dx squared. And the 1 comes down and we get a 6. So that's our second differential. Notice the 2 over here stands on top of the d, and this 2 stands next to the x. Now, another form of notation can also be used. Instead of writing y, we can write fx. Now, I can write the same thing out in using fx. And then to show that I'm going to differentiate fx, the differential is just simply f prime. And so we bring the power down and take 1 away from the power. And then to differentiate again, I use 2 dashes, and that means it's differentiated again, and we get 6. So that's notation. Okay, so we know how to differentiate. We know when you differentiate dy of dx, that gives you the gradient of y. What we now want to do is discover more about the curve. Now, there's something called stationary point, and stationary points occur when the gradient dy over dx, which is a gradient of y, equals 0. Okay, and so that would imply there's actually 3 types. We can have something like this, where you've got positives here, negative gradient there, and at this point the dy over dx equals 0. So here we've got maximum. This is called a maximum. Or we can have a curve where it goes down like this. So the gradient here is positive, here it's negative, got a dotted line, and here dy over dx equals 0. And this point here, let me just use a different color. Let's use, oops, we don't want that. Let's have a look. Right, this point here, just like this point there was maximum, this point here is called a minimum. So that's a minimum point. But we can also, and both of these are stationary points, but we can also have a point where the gradient doesn't change from positive to negative or negative to positive. We can also have a point where it just simply goes from positive to positive or negative to negative. So if we just put in, let me just put in a point there where dy over dx equals 0 at that point, and then we have the gradient here, it's positive, on here either side it's negative, and again at this point here dy over dx equals 0. Now these 2 points where the gradient doesn't change from either side, it's positive, positive, negative, negative, unlike the maximum or the minimum, excuse me, where it's positive, negative, negative, positive. These 2 points are called turning points. Let me use black, called turning points. Okay, so we know how to differentiate. We know dy over dx gives us the gradient of y. Let's look at how we can now use that. Firstly, it will be good to know where the curve peaks. So we know that there's a point called a stationary point, and this is a point where dy over dx equals 0. Now there's two types of stationary points. We have turning points, okay, or points of inflection. Now the turning points are, for example, points where the gradient turns. So you've got a maximum, or you might have a minimum. And let's see what's going on here. On the maximum, the gradient here is positive, and over here it's negative, and this is your point. Okay, so over here we know that dy over dx equals 0. Over here we've got a gradient which is positive, over here it's negative, and at this point again dy over dx equals 0. Now what's interesting is the gradient changes, it turns, it goes from positive to negative, negative to positive. Now when it does this, this is called a maximum. Okay, so that's a special word we need to keep in mind, and this is called a minimum. Right, so you might have met this in doing quadratics. Now a point of inflection is a point where the gradient doesn't change from positive to negative, so you might get something like this, okay, or even something like this. So if you've got positives, or you might have something like this, you've got negatives. Now over here we know all this dy over dx equals 0 at this point. Similarly here, dy over dx equals 0, except now the gradient changes, it just goes from positive to positive or negative to negative, and these 2 points are called points of inflection. So to summarize, we have stationary points where dy over dx equals 0, and they fall under 2 categories. We have turning points, which is a maximum or a minimum, or we have points of inflection, which look like that. Okay, so let's see how what we've just learned can be applied to work out the nature of some stationary points on this curve. So we've been given a task where we've got to work out firstly the stationary points and then find out their nature. By nature, what they mean is whether it's maximum, minimum, or point of inflection. So firstly, let's differentiate our y. So we've got 3 take away 3x squared. And then we know on a stationary point, the dy of dx equals 0. So we can set that to 0 and solve it. And so we get x squared equals 1 and x equals plus or minus 1. If we substitute the corresponding x values back into our y, we should be able to generate some more answers. So we should be able to get our y coordinates, sorry. So when x equals 1, y equals 3 take away 1, which is 2, so we've got a coordinate 1 and 2. And then when x equals minus 1, y equals minus 3 minus minus 1, which is minus 3 plus 1, which gives us minus 2. So we've got minus 1, minus 2. And so we've answered the first part of the question, which is about finding the stationary points on the curve. Now the next thing to do is work out the nature, investigate the nature. And there's 2 methods. The first method, I'll write this down as method 1, is to use a table. And with the table, the way it works is we'll look at the gradient on either side of a stationary point and look at how the gradient changes. So we know our x values are 1 and minus 1. So let's write that out. What we'd want to do is look at some values on either side. So if we've got minus 1 here, we'll probably want to look at minus 2, and then we can go to 0, and then it picks up on 1, and we probably want to look at 2 as well. So these are our x values, and we want to look at the value of the gradient for each of these x values. So if I just make a little table like that, and we can plug these x values into our formula for dy of dx and generate our gradient. So for the first value we should get minus 9, and for the second one we should get 0. Then we should get 3, and 3 take away 3 is 0 again, and then we put 4 in, and we should get minus 9. Now what we can see here is the gradient here is negative. Over here the gradient is 0. It's then positive. This means this value where we've got x is minus 1, which we've already recognized as one of our stationary points, that means this value here now goes from negative to positive, so it probably looks something like that. There's negative, there's positive, therefore this must be a minimum. Now if we look at the other side, let me just get rid of this red line here. Right, so that's not going away. Right, so if we look at our stationary point over here, where x equals 1, on either side we have firstly a positive, we then have a 0 gradient, and then a negative gradient. So on either side it changes, so that means it probably looks something like that. So it's positive first, then on the other side it's negative, therefore this point here must be a maximum. Okay, so we can therefore conclude that 1, 2 is a maximum point, and minus 1, minus 2 is a minimum point. So to summarize what we've done, we've looked at one method. There's another method yet to come, which allows us to work out the nature. By nature we mean whether by nature of a curve we mean whether it's a maximum, minimum, or point of inflection. And we do that by working out dy of dx. On a stationary point that's 0, we solve it, we find two values of x, substitute it, find two values of y, and we get our coordinates. Now to work out whether these particular coordinates are maximum or minimum, we can we can look at the gradient on either side. So from minus 1 we'll go up by 1 and down by 1, and we'll work out the gradient on either side and see that it changes from negative to positive, so therefore it looks something like this as a minimum point. And for the gradient where x equals 1, the stationary point, so where x equals 1, again we look at the gradient on either side when it's 0 and 2, and here we see it goes from positive to negative, and therefore it's a maximum point. Now there is a second method which we can use, and it's probably more commonly used, and it goes like this. So let's write down method 2, and we know our y equals 3x minus x cubed, and we know that dy over dx equals 3 minus 3x squared. If we were to differentiate this again, d squared y over dx squared will just give us minus 6x. Now the second method works like this. If d squared y over dx squared is greater than 0, then this means this particular point is going to be a minimum point. If, however, d squared y over dx squared is less than 0, then it's a maximum point. If dy over dx does not equal 0, and d squared y over dx squared equals 0, then we have to do some further tests, and at this stage it's probably best to use the table in method 1. Whatever method you use, just make sure you show your full working out. So we know from the previous examples that our stationary points were given by 1, 2, and -1, -2. So let's test them. Right, d squared y over dx squared. So for the first one, okay, d squared y over dx squared equals -6x. This equals -6 times 1, which equals -6. This is less than 0, and therefore this point has to be a maximum point. Let's test -1, -2, and then this gives us d squared y over dx squared is -6 minus 1, which is 6. Since this is greater than 0, we therefore have a minimum point. Okay, another way we can use differentiation, in fact it's the way Newton sort of envisaged the whole thing, was to look at acceleration, velocity, and displacement. So from physics we know that the relationship between the three is that velocity is a rate of change of displacement and acceleration is a rate of change of velocity. So in here we have a question where we're given, we're not using x's and y's now, we're using s's and t's, and velocity and acceleration as well, so v and a. The displacement s meters of a particle from point P at time t seconds is given by this equation. Calculate the velocity and acceleration of the particle after 2 seconds have elapsed. So let's set up some equations first. We have s equal to t cubed take away 4t. Now ds over dt, the rate of change of displacement, which is v, is given by 3t squared take away 4, and then dv over dt, which is the acceleration, is given by 6t. Now, so now we have equations for v and t, and we're told to work out the velocity and acceleration for t equals 2. So we can substitute 2 in there. So at t equals 2, v equals 3 times 2 squared take away 4, which gives us 12 take away 4, which gives us 8. And also at t equals 2, a equals 6 times 2, which is 12. Probably good to put in the units. So for velocity it will be meters per second, and acceleration meters per second squared. Okay, so let's look at a practical example now of how this can be applied. This question here tells us that there's a rectangular sheet of metal of length 1 and width 1, and the squares cut from each corner over here. Now this is an important word because it tells us it's actually a square. The sides are then folded up to form an open-topped box. Find the maximum possible volume of the box. Now it's probably good to just draw a diagram like we've got over here. And the fact that we've got 1 times 1, we can call some length x, we know it's a square. Okay, and so therefore the difference over here, if this is x and this is x, then that forms 2x, and the remaining distance must be 1 minus 2x. We can then start modeling. They want us to work out the volume, and in fact the maximum possible volume. So let's begin by working out, say, the length over here and the width. Because it's square, it's going to be the same. So we can write down the length equals the width, and this equals 1 minus 2x. We also know that the depth equals x, and so the volume equals x 1 minus 2x. And in fact it's x 1 minus 2x times 1 minus 2x. The reason we've got that is we've got length times width times our depth will give us the total volume. So we've got an expression for the volume. Now if we were to expand this out, we should get V equals x minus 4x squared plus 4x cubed. We can then differentiate this, so we can work out what dv over dx is, and you might want to pause the video and have a go at that. So we get 1 minus 8x plus 12x squared. Now since it wants a maximum possible volume, we have to set this to 0 and solve it. Again, you might want to pause the video and have a go at this. If we solve it, we get we should get x equals a half, or x equals 1 over 6. Now we can then substitute those values of x back into v, into our expression for v, and we should get v equals 0 for half, or v equals 2 over 27. In this case, the 2 over 27 must be the maximum value, and so therefore the maximum volume equals 2 over 27. We should also put the units down when we look at lengths, areas and volumes, and we're working in meters, therefore it's meter cubed. Right, as a test question for the form, what I'd like you to do is for y, which equals 3x minus x cubed, I'd like you to find d squared over the second differential, d squared y over dx squared, find an expression for that and enter results in the form.